Hi, welcome back. Let's dive into what even is classical MAPF and let's define the problem. So MAPF literature is an extremely fast-growing area. There is a lot of research going into this and the family of algorithms continue to explode. However, there is this idea of the original classical MAPF problem, which forms like this fundamental backbone for a lot of the rest of this work. And then we really need to define these terms, right? Because when you're trying to compare algorithms and also to see which ones kind of fit your target problem, well, we need to define some of the nomenclature as well as what actually is considered in the problem itself. So classical MAPF, as we're about to define, is a very, very simple bare bones problem. It's the core idea, the core principles under a lot of these applications. It does not include things like turning costs, angle pathfinding, diagonal movement, continuous time, continuous movement, lockstep movement, agents with size, a million other variables that we could introduce to the problem. So let's get to it. What are the actual rules and assumptions we're making within classical MAPF? So the very first one is extremely simple, drawn up like a little example from over here. The colors, I think, are a bit difficult on the light board, so hopefully I can fix that a bit in post. But we have essentially, unfortunately, the pink has to overlap because I ran out of marker colors. But otherwise, we have a bunch of agent start and goal locations. The difference, of course, in multi-agent pathfinding is that now we need to actually plan agents in collision-free paths according to time, right? We'll talk about how collisions are handled down here at the end, but you can start to see that in congested areas, things can start to become quite difficult. The very, very first thing is, well, we have defined over here that each agent has a specific start and target location. Okay, so they start explicitly in one location and they always just have one target location they're going to. This isn't some lifelong problem where you get there and then you get a new thing. That is, again, another additional step above just classical MAPF. You just need to get them to go exactly where they need to their one target. The other aspect of this is that essentially it's a very, very simplified problem. We have what is essentially four connected movement. So you can only move in the four cardinal directions, right? There is no diagonal movement. This is the standard version of the problem. So to write that down explicitly, it is four connected traversability. Okay? Now, the thing here, though, is that we do have, because we're working with time, agents are now moving through time. We're getting them to avoid each other. Well, agents now have a new action they can do, which is essentially to wait. Agents can always just stay put at their exact same location, right? So they occupy the same XY location for the next time step as well. That's the waiting move. So agents can always wait. That is a new version, a new action that is always accessible to the agents as well, of course, given that there is no collisions occurring because of this. And then finally, really, it's just the idea that we're going to simplify the problem. Each of these actions are going to have the exact same cost, right? And that kind of is built in with, thankfully, because we don't have to deal with the diagonals. All of the cardinal straight moves just have a cost of 1 in usual pathfinding. We're saying here that the wait action just always has a cost of 1 as well. So uniform cost actions. All actions cost the exact same. And this is really the basic foundations of classical MAPF. I think it's extremely easy to understand. It's a very core fundamental problem, and it still is, as we're going to see, actually pretty difficult. And we're going to have to devise a bunch of very clever algorithms to try to tackle this through coupled approaches, decoupled approaches, optimal, suboptimal, a million other things. So let's very quickly talk as well about collision handling, though. So there are two types of collisions, right? Obviously, agents cannot occupy the exact same location at the same time. So if you draw out some paths for these agents in the grid here, well, we would see that when they plan, they are both going to be interacting and essentially colliding at this joint location. They're both trying to get there at the second time step. Agents cannot occupy the same cell at the same time, obviously, but we're going to define these as two different things. So to draw that up, there's essentially two cases, right? So there's one where you have this connectivity, and then there's another version where an agent is waiting. So what we have is that if we have an agent A, right, and an agent B, essentially they can't both go occupy the same cell at the same time. In this instance, they're both trying to occupy the same cell. That is illegal. Now, we also have a very similar concept. Imagine one agent B is already at this location and it's waiting. So maybe I'll draw that with a loop. And then, of course, another agent is trying to enter this location. Right, so this is also illegal. So all of this together is known as a vertex conflict. In the language of graphs, of course, we have vertices and edges. Well, we both can't occupy the same cell, the same vertex at the same time. This is a vertex conflict. The other version of this is, I think, very intuitive as well. But it is different. Now, this is only entering into the equation because we now have these moving agents and we have this time at play. So agents can now also collide when they cross each other, right? So not only is it enough to just check that they're not at the same location, they can't be at two adjacent locations and swap, right? If you have two trains moving on the same track, of course they're going to hit each other, right? Agents cannot cross directly, especially in the definition of what is classical MAPF. So to draw that up, it really is the similar idea, but we have our two nodes. We have a node A here, moving this way, and we have an agent B moving the other way. This is a vertex, this is what we call an edge conflict, which I'll write here as well. Edge conflict. Okay, they cannot cross. That makes sense. I think that's very intuitive. Now, I'll also draw up one third case. It's a bit different, but it's just really important to know because you can consider this based on different problems. Classical MAPF actually allows something called lockstep movement. So lockstep movement is when we have essentially the idea that agents can go around and follow the agent in front of them exactly, right? They perfectly fit. So here we're about to have a whole bunch of agents. I'll just draw it in the same color because, no, I'll change color. So we have agent B. Now, this is the test of does green look different than yellow? C. And then we also have another agent D going this way. So this is what I would be describing as lockstep movement. Essentially, this is a situation where you have a bunch of agents that are perfectly following. So if agent B was at this location, right, at the current time step, the moment it's moving out, we have like this, we're allowed to kind of like shift, right, like the rubber bands trailing immediately behind each other. Now, in certain problems, this doesn't really make sense based on the way agents move. And then in other types of problems like railroad networks, for example, well, trains often have to maintain a safety distance from other trains, so you would not be able to do lockstep movement. So this is just something, I'll write it down. So this is lockstep movement. Lockstep movement. And then is allowed. So this one is a big tick, and then these are disallowed as movement. These are collisions. So now we're going to jump over here because not only are we interested in adhering to the rules of the world and making conflict-free paths, well, we need some way of actually measuring which path, which solution is better, right? Which version of all the solutions is better for us. We're still doing an optimization problem. So that's where the objectives come in. We need to define some way of judging the value of a solution set or a candidate solution. Or of course, during search, actually a partial solution, which one's looking more promising than another in terms of some form of objective. So there are a couple that we essentially use as the primary avenues within MAPF. One of these is sum of costs. So here, very aptly named, we just want to minimize the sum of all path costs. Right, so for all agents, all of the paths that we've computed, we sum up their costs, and this is our objective. Note that what's a really, really important distinction is this is called sum of costs, okay? If you're familiar with the literature at all, sometimes you see another metric pop up, which is called sum of individual costs, okay? I would argue oftentimes they're used interchangeably. I think sum of costs, SOC, I'll write that as well because this is often just called SOC, maybe with a capital O as well. This is, I think, the standard version of this. Sum of individual costs may refer separately to the idea that the paths were planned according to a greedy policy, ignoring collisions, ignoring all other agents, right? So that could be a metric to help guide you sometimes towards a solution with high quality paths, right? They're close as possible to their optimal version. However, the default, the standard way of doing this is just SOC, which is to actually minimize the collision-free paths, because that's usually what we actually care about. Now, the other one here is called make span, okay? So the other version of this is a very, very common objective in real-world problems, of course, is you're not just trying to minimize the actual amount of total fuel, right, that maybe your trucks have used, your fleet in delivering these packages or whatever else it is you're doing, but also it's like the main objective could be instead that I want the full operation, all packages to be delivered within the earliest time possible, right? So what you would be looking at then in terms of the make span is the arrival, is minimize the latest arrival time. Right? So what is the time step that your last truck, your last agent arrived at its destination? This is a very, very important metric as well. You'll often see that the two of them are very much joined, intertwined. So often optimizing for one has a very positive correlated impact with the other. But we'll see that that is absolutely not always the case. And solutions, you can't just get free lunch, right? Essentially, you're going to have to pick one of these objectives and use that as what you're actually optimizing for. And it absolutely can be the fact in practice that when you start optimizing for sum of costs, your make span will become worse. They are, however, often correlated. So oftentimes, you can kind of improve both together. So it goes hand in hand, right? Solution costs being smaller often means the make span might also be smaller. So forth. You choose based on which of these is more important for your problem. So with all of that said, this is Classical MAPF defined. These are the fundamental core ideas, and let's dive in the next videos into how we're going to actually go about writing some multi-agent MAPF solvers. Please join me there, as the first one we're going to look at is the most intuitive MAPF algorithm I think you can come up with. It's extremely simple. It is strangely very, very performative as well, much more than I think you would actually expect. We're going to be looking at prioritized planning. Join me there and see you soon.